Okay, now uh, as we discussed last week, we have now Taylor series, and later we're going to see the Maclaurin. So the Taylor series is actually, we are going to see the series that is built up from the derivative of the functions, okay? And then we put all the information needed, okay, as this, okay, this is the series. So we put all the functions and its derivative on each coefficient, okay? And simply we can say the variable x that is going on here is actually, if you remember the very basic part of the series, we learned about the geometric series, we learned about the x squared, right? The x squared, and or x with power of n, okay? And then we see that when we have the ratio that is x, then x is we can say less than 1. We can see a build up this from the series that start from 1, x, x squared, x cubed, and so on and so forth. Okay, and then we can also mix that up with the derivative, okay, for that function. So for every function that you may find, and you can find these relations, and it seems that if we can relate the function with its derivative, we can make out this the series. Okay, so we call this the Taylor series. Okay, now just to make sure that we understand, if the a, so if a equals 0, okay, then we call this is the Maclaurin series. Okay, basically the same series, but the difference is we just substitute 0 into a. Okay. And later we are going to see several functions that we can maybe we can find the Taylor or the Maclaurin series. Okay. Like for example, the most frequently used functions is the exponential, the trigonometric, the logarithmic. Okay. That is some examples. Okay. Okay, let's see some example. Remember that from the previous sections, we know that if we have this function 1 over 1 minus x, this is, we can represent as a power series, that is x with power of n, and this is equal to 1 plus x squared plus dot dot, and the ratio is less than 1. So according to what we have done in Maclaurin, okay, when the a is equal to 0, let's say we are going to see that if we take this, and then if we plug in 0 to this functions, this is equal to 1, right? And let's derive this. And since it's minus x, so it's going to be positive like this. And then the value is also 1. Okay? And then if we take the second derivative, it's become, let me write in terms of 1 and then multiply by 2, because from the 2 from the bottom, and then 1 minus x, and it's become minus 3, and this become 3. And then second derivative, this is 1 by 2. And let's say we take the third derivative, and this become 1, 2, 3, and the denominator becomes power of 4. Okay. Okay. And in general, we can write f derivative n is equal, if we look at the pattern, it seems that this is going to be n factorials on the numerator, and the below part, the denominator is 1 minus x, and it's plus 1 of the numerator, right? So we can take n plus 1. And when x is equal 0, this is going to be this n factorial. So when we compute the coefficient, which is f derivative of n of 0 over n factorial, this is the one that we discussed last week, right? Then this will be n factorial divided by n factorial, which is 1. So this is true that we can rewrite the functions 1 over 1 minus x through the Maclaurin series and say that this will be, we can write the derivative 0 of x with power of n, or we can say that this is simply so we can see the 1 over 1 minus x through the lens of the Maclaurin series. Okay. So now you can have a general approach to a functions. Okay. If you want to represent the function with a series, you can go directly through the Maclaurin series. Okay. You can try the Maclaurin series and then substitute this variable with 0. Okay. But of course, we can have two approaches. Like you can go directly write this like usual geometric series. You can see from that part, or you can also prove the functions using the Maclaurin series. Okay, and then plug in 0 to find the coefficient, and then we can see how it goes from this coefficient here. That is going to be equal to 1. So the whole thing here, the coefficient is equal 1. So we can describe that the functions is equal to sum of the x with power of n. Let me write the original Maclaurin to help you to realize that the Maclaurin is representing the function of x as a series f derivative of n of 0 over n factorial x with power of n. Okay. This is when a is equal to 0. So if you remember the Taylor is f and a over n factorial, and then this is x minus a with power of n. And that's the Taylor. So the Maclaurin, you just put a into 0. Okay, so that's it. Okay. And since the Maclaurin, why does the Maclaurin has its own name? Because I think one thing to see, the Maclaurin is more practical, and we can see most functions can be related to the Maclaurin easily, okay, rather than the Taylor. The Taylor is more like to analyze, because it still have a, which is when we still have a, it means that the convergences is still on some interval, right? But in the Maclaurin, we can see that it's directly a equals 0, so it doesn't have any interval convergences. Now let's say we are going to see the, let's say now we have the functions e to the x, e power of x. Okay, we know that if we derive e, no matter how many times we derive, it will be still e to the x, right? So we can write the f with derivative n of x is still e with power of x, right? So if we take the value of 0, then it will be 1, right? For all n. So the Maclaurin for e to the x we can write sum fn 0 over n factorial with x power of n, or simply we can write sum over n factorial, or let me write maybe going down here. So this will be equal to 1 plus x. Let me write over 1 factorial so you can see the pattern. So x squared over 2 factorial and of course, if the questions also ask the convergences, you can check the ratio test. Okay, so sometimes maybe we because we learn the power series, okay, we learn how to find the convergences, and sometimes the question for the Maclaurin or the Taylor also checking the radius of convergence and the interval of convergences. So if we want to check, the R, okay, or radius of convergences, then we can take the ratio test, and let an is x with power of n and n factorial, okay. And then we take the limit an plus 1 divided by an, so this will be x n plus 1 okay. And then by taking this, maybe let me write downside here to make clear. So we can cancel x power n, so this will be x, and n factorial with this, so we have limit or we can write this is x limit and we could see that because the limit itself is always 0, right? It's always 0, so any x is possible, right? So we can say from this conclusions, so series converges for all x. So R is for every x. But again, we need some proof for our Taylor or Maclaurin series. Okay? Because if we take this, okay, if we want to represent the functions as a series, okay, of course, if we write directly Like for example, e to the x equal to this, sum of the x to the power of n over n factorial. Still, we really cannot say in exact way that is truly exactly equal. What we did here is actually through concept of limit, right, in calculus. So we need some proof, okay, to make sure that how close that the functions with the series in terms of graph, in terms of the value. Okay, so that's the next question. So when is the function represented by the Taylor series? So we are going to see, maybe take some samplings and take some parts, and then maybe see the graphs, okay, how close that is. Okay. Okay, now let's get into what does it mean. Okay, let's write, before we go to the graph, let's write the Taylor that we know. That's the Taylor series, right? So to observe or to analyze how close the series with the functions, we are going to see the fx as limit of sequence of partial sums. Okay. So what does it mean? So we are going to slice the series and make the sum of each one, okay? each one of the sequence. Okay? If you remember the S1, S2, S3, let's do that. But let's rename the sum as T n of x. Okay, let's rename it the partial sum. So the partial sum is equal, and let's derive from I equals 0 until n, because we want to limit the number until some n. So f derivative, okay, and change n into I, which means that this denotes that it will be not abstract value, okay? Because if you take as usual n until infinity, this will be an abstract value until infinite, right? So we want to make sure that we can evaluate the numbers, okay? Okay, let's take a few terms. From 0. We can take from 0. We can take this as fa.
and then plus, let's derive f prime a, and then this is 1 factorial, and then x minus a, and then plus the second derivative, and since it's until n, so let's just make dot 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 until the fn. Right. And this will be n factorial and x minus a with power of n. And you can say this Tn also denotes that this is n degree Taylor polynomial or polynomial f at a. Okay, to simplify this Taylor partial sum, so we can say this is a Taylor partial sum or n degree Taylor polynomial f at a. Let's say we are going to evaluate a at 0 to get into Maclaurin, and then maybe take example the function as the e, like the previous example e. Okay. So we take the let f of x equal e and a equals 0, so to make it Maclaurin. So remember that e to the x will be the same for every derivative of its functions, and when a equals 0, it means that it will be equal 1. So simply we say that when we have t1x, so this will be 1 plus x, right? Okay. And then when we have t2x, this will be 1 plus x squared over 2 factorial, right? If you want to make sure, you can write this is e to the x, f prime x is also e to the x, f double prime x is also e to the x, and we can write when x equals 0 it's 1, this is also 1, this is also 1, okay. And then you substitute to the formula. And then maybe let's take the third one. It's 1 plus x squared over 2 factorial, and adding the cube over 3 factorial. Okay. And this is something that you can take into calculators or graphing calculators, or taking into the website to see the graphs. You will see that the graphs will look like this. Okay, let me take this, make it look a bit smaller. And what we are doing now is we are going to see how this t1, t2, t3 compare with the original function e to the x. Okay. So if we are going to see this part here from this line here, we are going to see that all the t1, t2, t3, and at this interval, it's going to get closer to the e to the x. Okay. Of course, the particular interval is maybe around here, okay. The one that is really close and it's I think getting in line with the sources. Right? So it suggests that when we increase the number, when we increase the n, maybe we can predict what will happen with T4, T5, T6, and it's going to be equaling to the sources, to the original e to the x. This proves that the more numbers we input, the more n we input, the more that it is going to be equaling the original functions. Which means that if we increase the number n as going to be infinity, we can see that the f of x at certain point, we can take the limit as it's increasing, getting larger, that this is equal. Okay, so with the concept of limit, that this will be equal. Okay. And of course, still in reality, there will be like some sort of gap, small gap, that we call the gap as error, right? Between the exact value and its limit. Okay, so and we can rewrite the r or the error. So let Rn is the gap between these two. Or we can write the fx as the t plus the r. And in polynomials, we remember that the r is called the remainder. Something that's still, when we divide, it's still there, right? Still left on the equations. So it's not completely divided in polynomial. So the idea is for that this remainder to getting as small as possible or getting close to zero to make the error is as small as it can. Okay. So we need to make sure that the limit, or maybe let me write this a bit down here. So if we can show that the remainder when we take the limit and increasing the n, if we can show that this error is getting close to zero, then of course this will show that limit is the subtract between the functions and the error, or we can say f of x minus limit. So if we can show that this is zero, then it's true that the limit of the Tn is equal to f of x. And you can just see the conclusions here. Okay.
And then one way to see this remainder is with the inequality, the Taylor inequality. We are not discussed much on this Taylor inequality. This is just to show you that we can approximate. Okay? So we can approximate the Taylor. So this is going to be in approximating functions. Okay, if we have time later, we can go back to this inequality. But this is just to show that when we have some certain value m and d for each f derivative and the interval x minus a, then we can rewrite the remainder using the terms from the Taylor, okay? Using the terms for Taylor and exchange the derivative of f with m. Okay, this is just to limit the derivative of f because it's going to be less or equal m. And then exchange the interval and write the interval as a d. Okay, this is for the ratio. Okay, the ratio. So how we are going to use this? This is mostly we are going to use this in approximations. How when we approximate some certain functions, we can do this method. But I think I will not be focusing on this approximation for now. Okay, now remember that the e to the x, as we mentioned before, I forgot to mention, the e to the x is a sum, right, of x power n divided by n factorial. And we know that from the previous radius observation or radius analysis that we know that this is going to converge, right? It's going to converge for all x, right? So we take the ratio test and we say that this is converged, right? When the series converge, if you remember, when the series converge, we can write that the limit of its sequence will be equal to 0, right? So because it's converged, then we can know that the limit should be 0. Okay? And remember, if limit 0, it's not necessarily to be converged. Okay, just to make sure. Okay. Okay, let's move to next page. But if you want to write notes, you can write for a while.
Okay, let's say we are going to take some examples and let's look on how the functions for other functions. Okay. Well, let's start from the f of x equal sine. Okay, so start with the Maclaurin series for Sine X. How we develop the terms. So you may take a few terms, take some few derivatives. Let's say 4 terms. 4 in derivative, usually we write 4 and then with a bracket like that. It means it's the power 4 means the derivative, a fourth derivative. Okay. And then take x equals 0. Okay, and then you will see the coefficient becomes 0, 1, 0, which means that the terms can be removed because of 0, right? Okay, I think we can take a break and we continue after the break. Okay, let's continue. So for the Maclaurin series, so we can remember the idea is just to rewrite the functions, and we can write f0, f prime 0 over 1 factorial plus f double prime 0 okay. And since we have when n equal 2 and n equal 4 is going to be 0. So, and f0 also 0, so we could say this is 0. So this is 0, this is 0, and the fourth will be 0, right? So we can write x, okay, minus, because minus 1, x cubed over 3 factorial, and we know after 4 we have plus 5, and then after that is another negative. And then from this alternating series we can write this is equal to the sum if this is equal to 1, okay, if this is equal to 2, okay, and this will be, 2n plus 1 factorial. So set n 0, it's 1, n equal 1 is 3, so it's okay. Because it's 1, 3, 5, 7, it's odd number, right? So x 2n plus 1 to make it odd. So we can write sine x as this sum. And if you want to prove with the Taylor's inequality, to find the error, to find the limit of the error, the remainder, we can do that as well. First is taking the, if we look at this pattern, the functions become sine, cosine, which have the maximum and minimum number 1 and -1, right? So f n plus 1 of x is either plus minus sine x or plus minus cosine x, right? So if we take the absolute value, so the maximum number will be 1. So we can let m equal 1. Okay. So this is going to prove that the error, absolute value of the error, or the remainder, is always less than m over n plus 1 factorial x n plus 1. And since m is equal 1, so we know that this will be x n plus 1 and this limit is equal to 0, right? Since it has the factorial on the bottom. And by squeeze theorems, then limit as n getting larger for the Rn x, this is also getting 0. So this is just to prove that the sum of its Maclaurin series is equal. Okay? So sine x is so this is to proving that fx equals sine x is equal to sum of its Maclaurin. But the one that I need to emphasize is the way we build the Maclaurin. Okay? So if you are given a function that perhaps it's going to be, it can be adjusted as a Maclaurin series, the first thing you can do is you need to write all the derivatives, right, when it's equal to 0, the x equal to 0. And then you write the pattern first, okay? And then figure it out from the pattern how the sum will be. Okay. Or else, if you want to just memorize this part, I think still okay. But we are going to have at least 5 or 6 basic Maclaurin, including the sine and later the cosine, the tangent inverse, the ln. Okay. Okay. So this is for sine x. Okay. Now, if you would like to know the Maclaurin for the cosine, for example, fx equal cosine x. Okay, you can start build up. Like usual, you can take the f prime x and start writing all the necessary coefficient. And we'll see that the pattern will somehow complementary with the sine. So for sine, it starts from 0, 1, 0. This is start from 0, 1, 0, negative 1. Okay. Other methods that I think quite interesting and it's still related to the previous sections is I think we can take the cosine as a derivative of sine, right? So we can focus on the pattern on the sine that we have written here. Okay, so let me just copy this. So this is going to be ddx of the sine. So this is good. So we can just take derivative for each of terms. So this become 1. And this will be negative 3x squared over 3 factorial plus 5x to the power of 4 over 5 factorial minus 7x to the power of 6 divided by 7 factorial plus and we can simplify the factorials. Okay? So we can simplify the factorials. When you write a little bit to the left. Okay. So this will be 1 minus 3 will be cancel out, and this will be 2 factorial plus x power 4. This is 4 factorial negative x with power of 6 divided by 6 factorial plus . Okay, and then from this pattern you can somehow look at the sum. It's alternating series. So alternating, and then it's going to be an even number. So we take 2n and 2n factorial for the denominator. Now you can check the other functions as well. For example, you can check the so far we have the e to the x, sine x, cosine x, also the 1 over 1 minus x. We have done that. And if you remember from the previous sections on the representation of functions as a power series, we developed the ln, the logarithmic, and the tangent inverse as well, right? And the result's still the same, but we can also make it into Maclaurin. Okay? So you can have options. Okay? You can just take as a regular representation of functions as a power series, as the previous sections, or you can develop the Maclaurin series to write the pattern and find the sum. Okay? Okay. Okay, now you can see some of the conclusions for all the Maclaurin series. Okay. So start from the very basic one, 1 over 1 minus x, the e to the x, sine x, cosine x, the tangent inverse, the ln 1 plus x, and the binomial theorem, which I think we are not discussing very often at the the bottom one. So I think we can just focus on the 6 basic functions up until the ln. So from the top until the ln here. This one you can take a look and observe, but I think we don't really have much conversations for one of these functions. I think you can also compare the results. Like for example, the tangent inverse and the ln. We can compare these two with the one that we've done with 1 over 1 minus x, right? The previous sections. The result should be the same with this, the sum. It should be the same. But how we get this through Maclaurin is we can get the pattern first, and then we simplify and then conclude the series, okay? And then pattern and conclude the series. Yeah, the binomial. This one? Yeah, the binomial. chain. But we don't. I think we don't really have much conversation. So this is to show this can also be done through the binomial theorem. I think you can focus on the number 1 to number 6. I think it's already a lot. So yeah. If you choose to memorize, which I don't encourage you to memorize, maybe focus on how to build the Maclaurin. That's, I think, the important one. That doesn't mean the memorization is bad. I mean, you can memorize 1 or 2 that's simply or easy to see. Like the, I think e to the x, I think easy to follow, because e to the x, if we derive, it's still e to the x for all the terms, right? And I think sine and cosine, easy to conclude, because sine, you can choose sine or cosine, and then you can just derive to make the other one. I think that a little bit difficult, maybe this one, but I think still the tangent inverse we can still derive, and the form is actually similar to what we have done in the first one. It's going to be 1 over 1 plus x squared. We can change x with minus x squared, right? So if we change x to minus x squared, then you will see that it can x squared 4, 6, and it will be similar to what we have in the tangent inverse later, right? Okay, the ln is, we can also see this is coming from this part as well, and we integrate, right? We integrate.
Okay. Yeah. Maybe take a deep breath first and see if we can absorb the content. Or maybe instead absorbing, maybe the content will be evaporate. We call this Maclaurin is really the basis, okay? Because if, for example, if other functions that include this and maybe it has a different forms, then we can represent the series within our knowledge from this basis. We can rewrite the new sum. So, for example, right. Let me write. For example, if I take f of x, if you write x cosine x, okay, we know the cosine x has its own Maclaurin series. Okay. So we know that the cosine x has the sum, it's even number, right? An even number factorial. Okay. So the x then becomes, we are just going to multiply, right? Multiply the sum. So we can take this and write the sum. This is -1 and x 2n plus 1 and then 2n factorial, right? And for example, if we have another terms, if f is ln 1 plus, let's say, 3x squared, which means that we are going to replace x at this basis, the ln, with 3x squared. Okay. So we can start write ln 1 plus x. We can just write the alternating and then over n like that first, okay? And then substitute sub x with 3x squared. So ln 1 plus 3x squared this is 3x squared n, or this is 3 with power of n, x power of 2n over n. Of course, the other question that might be asked is maybe asking the convergences, in which you can do the ratio test. Okay. Or you could find the convergences through this this conclusion here. We have the conclusion already on the right side, and you can use that conclusions. And then, or I think you can just take ratio test to make sure. Based on the conclusion, we can see this converge. Okay, so x need to be, so this is the R. Okay,
I think for the cosine, it is going to be for all x, right? And the other type of question that might be asked is, you are given a series, and then you need to represent the series as a function. So reversing the process. And reversing the process means that you need to aware of the basis Maclaurin. Okay? Because if not, then you will find the relations will be very difficult. I think we're going to see some example. Then maybe tomorrow I will give you another example and move to another chapter. Okay. So this is chapter 11. So we move to chapter 12. But I think I will make like a summary for chapter 12 because it's about factors. So I think we just give you some quick review. And hopefully you don't really need much notes for the chapter 12. The only notes that I want to emphasize is the last two sections, and that's it. And we move to chapter 13. So I think we are going to finish chapter 12 and 13 by this 2 weeks. Okay. Hopefully. And then after that, we can move to chapter 14. Yeah, still. Yeah, compare with the early part of the chapter 11, the Maclaurin part is a little bit. So I think from the chapter 8, the power series, there's 11.8, 11.9, and then this Taylor Maclaurin. It can like the content difficulty is significantly rising. Okay. Yeah, because it's going to be you're going to see a lot of algebra manipulations. At least from this, if you see from this sum, okay, the way you adjusting your terms, okay, if you're not finding your way, and then you will find it's difficult to relate this sum to the basis. Okay. Let me give you a quick example. Okay, let's say we are having the sum Okay, let me give you this. Okay, and the question is, find the function represented by the sum. Which means that we need something from this sum that can be related to the Maclaurin basis.
Oh, I think
right?
Like the power n, x power n, we can connect it to x power
Yes,
n.
yes.
So we know that 2x is the...
We can exchange that. We can imagine that if x, and then we can find the pattern, right? Okay. So one way to see, we can see the 2n and x to the power of n as one part. So we can take this and write, let's say 2x power of n, or even we can incorporate the negative. So we can put here, because it has the same n, right? So we can also take it into one bracket, negative 2x with power of n over n factorial. And if we remember, what is e to the x? This is x with power of n and then over n factorial, right? So this is actually e with exchanging x with negative 2x. So we know this is the functions. The function for this case is e with power of negative 2x. So since and then okay, another example, if we need to find the sum, okay, so find the sum, and we are given the series with its sequence with the, let's say this sum, okay, first thing is we need to observe what kind of series, and we need to write in terms of sum, the summations, okay, using the sigma notation. So at least there are two steps. So first, observe the sum. So write the sigma notations. And look at the pattern. First, it has the alternating, right? It has alternating series. And then it has 1, 2, the first term here. 1, 2, 3, 4. So it will be the denominator is n. And then multiply with 2. And then 2 squared, 2 cubed, 2 to the power 4 is becoming geometric. So we have n multiplied with 2 with power of n. But since it starts from I think n equal 1, so we need to adjust our alternate signs. So we can say this is n minus 1 and starting from n equal 1. And then further, we can write down the sum this is half with power of n and over n. Okay. If you look at the and the terms that we've got from this series here, we got this particular terms for ln, right? Remember, this n equal 1 is getting because it's because of the integrations, right? So we can let the since so we can take this, then the sum is ln 1 plus x with x equal 1 over 2. So we can write down here that maybe here. So conclusion, this is going to be ln 1 plus 1 over 2 or ln 3 over 2. And what's the benefit? Okay, so I think at the end of the day, why we need to have this Maclaurin series. So one way to think, if you remember, in calculus we have some function that cannot be integrated because of the non-elementary. Right? For example, if we take the integrations, consider integrations of the e, we cannot integrate this, right? This is something that we call the non-elementary. So to set up this, since we know the Maclaurin for e to the x, we can set up an infinite series for this integrations, right? So we can set up that this is going to be, or this is going to integrating from, or let me write, maybe let me write here. So we want to know this, and we know this part is equal of sum so alternating, and we can take okay. So the integrations, we can take integrations and then write all the patterns. And then we can say it's constant plus x minus, it become cube 3 1 factorial, and then plus x5 is 5 3 factorial minus, and so on and so forth, and then plus, we'll see that this is going to be an alternate series with x to n plus 1 become odd number, and then this will be the odd number multiply the n factorial.
Okay, I think I will just end up until here. Tomorrow we are going to see some other examples, okay, also to prepare your midterm, and then going to the new chapter. Okay.